Hello viewers. In this video, I will discuss about crystallization of unicomponent magma. The outline of this video is: magma is hot, molten, heterogeneous complex mixture of silicates, solid fragments, fluids and dissolved gases, contain large quantity of water, reactive fluids and gases in solution. Viscosity of the magma depends upon volatile content. Minerals crystallize at variable temperatures and follow bounce reaction principle. In this unit, unicomponent and bicomponent magma systems will be explained using phase rule and equilibrium crystallization. Introduction: chemical constituent is present in a system of universe. To study more complex systems, consider addition, subtraction of constituents in system and explained by phase rule. What is system? System, it's a part of the universe and physically separable. What are the types of systems? Open system, energy and matter can be transferred in case of open systems. Closed system, only heat energy can be exchanged. And isolated system, neither energy nor matter can be transferred. Now let us talk about the phase equilibrium. Phase, the definition of phase: physically and chemically homogeneous part of a system bounded by an interface with adjacent phases is called phase. What is component? Smallest number of chemical constituents needs to make up all phases in the system. And third one is degree of freedom, which is denoted by small f. That is minimum number of variables that define a state of a system at equilibrium. Now I will discuss about the Gibbs phase rule. State of a system is described by temperature, pressure, composition, mass, volume and other independent properties. Gibbs phase rule was formulated and named after American chemist J. Willard Gibbs. It is used in determination of degree of freedom of a system F. Phase rule is applicable only to the heterogeneous reversible reactions which are in equilibrium, whereas other reversible reactions are studied using law of action. I am citing one example of Makapoi lava lake. Magma samples were recovered from various depths beneath solid crust and shown in this photograph. Here I am showing you pyroxene, glass, olivine. These are all minerals present in the magma. Here again the thermocouple attached to sampler to determine temperature is shown over here of the same area, and the minerals are glass, pyroxene, plagioclase. Both these figures, one is under cross section, the other one is under the plane polarized light. The temperature of sample versus present glass. How much glass is present is plotted against the temperature. You will find there is a gradual decrease in the percentage of glass with the lowering of the temperature. Next is the minerals that form during crystallization. Mineral wise, the plot is between temperature and the number of amount of minerals present in the magma. So olivine is maximum at temperature 1200 degrees centigrade. Again, with the decrease in temperature, the amount is increasing and finally it decreases. But other components like clinopyroxene, plagioclase, opaque, they simply gradually decrease with the lowering of the temperature, and the amount of glass is gradually increasing. The melt is actually increasing with the lowering of the temperature. Minerals that form during crystallization: olivine forms in weight percentage, maximum olivine forms at which shows high Mg content, MgFe content, whereas agate is slightly lesser than olivine and plagioclase both. Now crystallization behavior of melt. Cooling melts crystallize from a liquid to solid over a range of temperature and pressures. Several minerals crystallize over this T range and the number of minerals increases at T decreases. T means temperature. Minerals that form do so sequentially, not subsequently, with considerable overlap. Minerals that involve solid solution change composition as the cooling progresses. Crystallization behavior of melt. Melt composition also changes during crystallization. Minerals that crystallize as well as the sequence depend on the temperature and composition of the melt. Pressure can affect the types of minerals that form and the sequence. The nature and pressure of the volatiles can also affect the minerals and their sequence. Now let us discuss about the phase rule. Phase rule is equal to F is equal to C minus rho plus 2. F is equal to degree of freedom, the number of intensive parameters that must be specified in order of completely determine the system. F equal to degree of freedom, the number of intensive parameters that must be specified in order to completely determine the system. Phi, or in some books it is written P also, equal to number of phases. Phases are mechanically separable constituents. Phi and C is equal to minimum number of components, chemical constituent that must be specified in order to define all phases. 2 is the intensive parameters, usually temperature and pressure for us like geologists. These are the two components, two parameters which are commonly used. Now phase diagram is graphically represent P and T conditions under which various phases exist and transform from one phase to another. It shows stability fields and relationship between different phases as a function of pressure, temperature and composition. It consists of areas, curves, lines and points. Phase equilibrium experiments performed in laboratory to understand crystallization behavior of magma of definite composition under same pressure and temperature conditions. Constitution of alloys as a function of temperature at equilibrium is represented by phase equilibrium diagrams. Application. The pressure and temperature conditions of magma generation and modification are ascertained from melting of rocks, minerals under laboratory conditions. Here is the experiment which is carried out in the laboratory with the help of a experimental furnace. I am showing this diagram. The red color portion shown in this diagram is a sample actually, and sample is placed inside the graphite furnace, and this graphite furnace is heated at a very elevated temperature and under very high pressure, maybe 800 ton rem. So this is actually pressure temperature controlled experiments where the melting of the sample is being carried out. Here is the phase diagram which shows melting point, temperature and the composition of the constituents like the solid, how much solid crystals have been formed, what is the liquid temperature, what is the solid and liquid proportion of each components. That is shown over here with this diagram. Phase diagram of unicomponent system showing critical and triple point. You see solid, liquid, gas, they are placed or they join, they are shown with the help of three curves, three different curves, and these three different curves meet at a point called triple point. The solid, liquids, triple point and critical point system is completely in the melt form, and 100% melt field is separated from rest of the phase diagram by boundary called liquidus. Liquidus line separates liquid from liquid plus solid. The 100% melt exists above this line. Low temperature stability field for 100% solid is separated from high temperature condition by a phase boundary line called solidus. Solidus is the line below this liquidus fine line where 100% solid exists. Solidus line separates solid from liquid plus solid both. Three curves separate solid, liquid and gas phases. Triple point is the point where temperature and pressure which the solid, liquid and vapor phases can exist together at equilibrium. The end point of a phase equilibrium curve is known as critical point. Critical point is defined as the point at which two phases of a substance initially become inseparable from each other. Unicomponent magma system. First I will discuss about the unicomponent magma system. System having only one component is called unicomponent system. When C equal to 1, pressure equal P equal to 1, then if you put these values in the equation, F equal to C minus P plus 2. So 1 and 1 minus 1 plus 2 is equal to 2. Thus, as per phase rule, a one component system must have degree of freedom of 2. One component system requires two variables, temperature and pressure. Phase diagram of one component system consists of point, curves, lines, areas and represent a non-variant, univariant and bivariant systems respectively. SiO2 and H2O systems are examples of one component system. Here I am showing this one component system. You can see the area, phase and composition in the diagram. On my left hand side there is a system, water vapor phase ice system is shown here, and on my right hand side the same is shown here. For each area C equal to 1 and P equal to 1, let's apply phase rule on areas. F is equal to C minus P plus 2, 1 minus 1 plus 2 equal to 2. So each area is bivariant system and it is necessary to specify T and P to define a phase. So phase ice composition is H2O, water composition is also H2O and vapor composition is also H2O. Water. One component system forms three phases in equilibrium with ice vapor, ice water, water vapor and depends upon temperature and pressure variables. Vapor phase at different temperatures, when plotted against corresponding temperature, the phase diagram of H2O system is obtained and consists of three stable and one metastable curves. Water vapor consists or exist in its equilibrium along the vapor phase curve of water. At point D, water vapor pressure is equal to atmospheric pressure, that is 100 degrees centigrade at boiling point of water. At 374 degrees centigrade temperature and 218 atmosphere pressure, curve OB finishes at B, where water and vapor are indistinguishable. System has one phase and this point is called critical point. Applying phase rule on this curve, C equal to 1 and phi equal to 2, F is equal to C minus phi plus 2 equal to 1 minus 2 plus 2 equal to 1. Curve represents a univariant system. Ice and vapor phases exist in equilibrium along sublimation curve of ice OA in figure. The lower end of OA curve extends to absolute 0, that is at minus 270 degrees centigrade, where no vapor exists. In figure, the areas AOC, COB and BOA represent following phases. Crystallization of SiO2 system. In unicomponent system, silica has number of polymorphs, each with a definite crystal structure and stable under definite temperature and pressure range. SiO2 system consists of many phases. Stability field represents P, that is pressure, and T, that is temperature conditions under which each mineral is stable. Phase boundaries define limits of stability fields and conditions under which phases in the adjoining fields are coexisting. For any of the phases, pressure and temperature vary without affecting nature of phases. Here is the phase diagram of unicomponent SiO2 system with following phases are present: melt SiO2, low quartz, that is alpha quartz, high quartz, which is beta quartz, tritiumite, cristobalite, coesite and schistosite. These are the phases present in this diagram. You can see here the top one is schistosite, then below that is coesite phase, and below that you have alpha quartz, low quartz, high quartz, tridymite, cristobalite, and finally grey colored is the liquid. So the same thing is shown with color diagram also in my right hand side. And in unicomponent system, silica has number of polymers, each with a definite crystal structure and stable under definite temperature and pressure range. SiO2 system consists of many phases. Stability field represents pressure and temperature conditions under which each mineral is stable. Phase boundaries define limits of stability field and conditions under which phases in the adjoining fields are coexisting. For any of the phases, pressure and temperature vary without affecting nature of phases. Now let us consider a phase diagram of a unicomponent SiO2 system with following phases. Phases are present, melt is present, which is shown here with grey color, and composition is SiO2, low quartz or alpha quartz, high quartz or beta quartz phase, tridymite, cristobalite, coesite, and schistosite. These are the phases present in this diagram on my left hand side as well as on my right hand side. So at the top you have schistosite, then below that there is a line that separates schistosite phase from coesite phase, and below coesite there are two important phases, low quartz phase and high quartz, that is alpha quartz and beta quartz, and at 1100 degree temperature till 1300 or say for example 1500 degree temperature, you have a tridymite and cristobalite phases. On my right hand side, the same thing is shown with colored diagrams to understand in a better manner. The coesite, alpha beta quartz, cristobalite, tridymite and liquid. Now what is the interpretation of these two diagrams? How you understand from these two, what is the outcome of these two diagrams and what they indicate? At point X, P is 3, that is equal to 3, where high quartz, tridymite, cristobalite coexist, as high quartz, tridymite, high quartz, cristobalite and tridymite, cristobalite phase boundaries intersect. Let's apply phase rule. C equal to 1, that is SiO2, 1 component. So P plus F equal to C plus 2. So 3 plus F equal to 1 plus 2, F equal to 0. Therefore, X is an invariant point, means three phases coexist in equilibrium, but temperature and pressure are invariable. At phase stability boundaries, for example, Y in the figure univariant curve, therefore, F equal to 1 plus 2 minus 2 equal to 1. F equal to 1 means pressure and temperature are invariant independently. If temperature increases, P also increases, and vice versa on phase stability boundary, where these two phases coexist. For any point within a phase, Z marked in figure, P equal to 1, low quartz, and now F equal to 2 means it is bivariant field and temperature and pressure can change independently without changing the phase stability. In figure, shaded area represents high temperature condition under which silica is in liquid phase, that is melt. On cooling at X, that is temperature 1650 degrees centigrade and pressure 0.4 gigapascal, cristobalite starts to crystallize. On further cooling, system will reach cristobalite tridymite phase boundary at 1470 degrees centigrade, and here cristobalite transforms into tridymite. On continuous cooling at tridymite high quartz phase boundary, it will transform into quartz. With further cooling, it reaches low quartz high quartz phase boundary where high quartz is converted into low quartz. Two phases will coexist only at phase boundary during phase transformation. On decompression and cooling, the high pressure varieties of SiO2 such as schistosite and coesite will be converted into polymorphs at suitable temperature and pressure ranges. SiO2 system explains abundance of quartz as a quartz is stable polymorph of silica over broad pressure temperature range. The coesite and schistosite found at meteorite impact and thermonuclear bomb sites. Now listeners, let us summarize what we have discussed in this video. We have discussed 1 and 2 component magma systems, open, closed and isolated systems, Gibbs phase rule, rule governing melt crystallization, phase rule, that is Pf equal to C minus rho plus 2, magma generation, solidus, liquidus, triple point and critical points, unicomponent system, crystallization of alpha, beta, quad types, tridymite, cristobalite, coesite and schistosite in SiO2 system. Thank you listeners.